Hello and welcome to 20 Hex Minutes of Deep Tech. I'm your host, Stuart Cording, the electronics reporter. Test and measurement equipment has gotten ever smaller and even ditched the screens and buttons. Instead of a visual interface on a PC or a tablet, a PC or tablet provides access to configuration options and measurement results. One of the companies at the forefront of this transformation is Liquid Instruments with their Moku range of reconfigurable instrumentation. Not only do such tools replace upwards of a half dozen pieces of equipment on your workbench, they offer clever analysis functions and the ability to link instruments in chains. Researchers, scientists and engineers are thus able to build complex experiments and test setups at a fraction of what it would have cost a decade ago. Now, at the end of 2024, Liquid Instruments added an AI component to their tools. So what can it do that a traditional FFT block can't, and how will it help users with their test and measurement challenges? To find out, I've invited Jason Ball, instrumentation expert and engineer at Liquid Instruments, to join me for the show. So strap in for 20 Hex Minutes and don't forget to post your questions for our Q&A at the end of the show. So, Jason, welcome to the show. Great to have you here.
Hi, thanks. Hi, Stuart. Thanks for having me on.
And it's a very special day because this is actually the first ever 20 Hex Minutes in
Nice.
Deep Tech show that we're doing. So, thanks for being the first guest.
The guinea pig.
So, it's probably a good point in the show to start by explaining what exactly is the Moku devices that you have at Liquid Instruments.
Well, so the Moku is a range, as you said in your introduction, it's a range of reconfigurable test and measurement hardware. And so the idea is imagine a box. You've got lots of individual test and measurement boxes. You've got things like spectrum analyzers, and oscilloscopes, and AWGs. And typically in an electronics lab, all of these devices are separate. And in our case, we have hardware that's based on an FPGA. And now the great thing about FPGAs is that they're reconfigurable, and you can load different modules onto them. So the idea is that our hardware is based on FPGA, and all of our instruments exist as software modules that you can load onto the FPGA and use them as needed, or partition the FPGA into multiple slots and put the instruments into different slots. And then you can route the digital signal throughout these instruments as you wish, as whatever suits you at the moment. So the idea is it's trying to be extremely flexible and streamlined and replace a bunch of standard test and measurement instruments, but also some more advanced functions too.
So we've basically got a single box. It's sort of reconfigurable via a software interface. Now, you've been in the test and measurement business for quite a while. This isn't your first foray into instrumentation tools. Maybe just for those of viewers who've sort of maybe got a bit more background and those who maybe don't know the topic at all, why don't you sort of explain the traditional way sort of a test setup is created, maybe an automated test system with traditional instrumentation, and what sort of challenges Liquid Instruments saw in that approach to test and measurement that you want to resolve with the Moku?
Well, yeah. So as I not to belabor the point too much, but the idea is typically you've got a separate box that does a single function. So I need to output some type of signal to my system or to my device under test. So I typically use something like a waveform generator, which you can see in the graphic here that Stuart's showing. So you have an AWG, you got a waveform generator. Those can typically generate your output. And then on the input side, you've got things like oscilloscope, digitizer, spectrum analyzer. And these are what kind of captures any signal that comes back from your device under test, and you use it to analyze. Now, all of these boxes work, just fine individually. The problem is that, number one, they all need to be physically connected to each other and synchronized. Number two, they're all, unless you are very loyal to a particular brand, nobody makes all of these. So you're typically using a bunch of different manufacturers, which means that their interfaces and the way that you control them and adjust the settings and configure them is all kind of slightly different. And so typically, you would have to, make some kind of homebrew code. You'd have to, have all of these like Skippy commands kind of manually wrapped up. You deploy some custom Python function. And so it's just, it creates a lot, it's certainly possible. Everybody's been doing this for years, but it creates a lot of failure points, both from all of your physical connections going back and forth, from all the code that you have to write to kind of wrap all these instruments up, synchronization issues, it just being able to load all of these onto a single instrument, have them all connected to each other, all operating from the same clock, all digital interconnects between the instruments, and then all controlled through one interface. It just really, really streamlines everything. And from my personal experience, yeah, I've wasted a lot of time in my career, chasing down bugs, chasing down errors. Oh no, one cable amidst this rat's nest of cables is bad, and so it's causing some phase delay between some other signal that's like screwing everything up. So it removes a lot of those failure points in my personal experience.
One of the things you just said there I found quite interesting is a single tool. I mean, typically when you look at sort of I sort of go to a trade fair and look at some of the other instrumentation tool providers, test and measurement equipment providers. Inevitably, you're not going to get everything from one supplier. Right. So I guess there's also often challenges in trying to get tools from different suppliers working together, even if they do have sort of a standardized software interface. Would that be the case?
Yeah, and I mean, the Moku, of course, it has, can't do every single thing, possible in your lab. But we do have ways. We've got analog inputs. Our flagship model, the Moku Pro, has 4 inputs, 4 outputs. So if you need to connect it, input it from another device or output to another device, there's also a 10 megahertz reference clock on the back. So, we're not going to, replace every single. We're not saying that we're going to replace every single thing in your lab. Let me just get that out there. But the more you can compress things into a single device, and as you said, streamline everything through one interface. If you are still running the homebrew Python code, like we can accommodate that too. We've got APIs that can easily kind of slot into your whatever code you're running for your experiments.
Yeah. So essentially, we've got a hardware box,
Yep.
and if we go on the website, we'll see that there's quite a range of those, and there's some inputs there, there's some outputs there. They have different capabilities, and then inside the software, I have all these different instrumentation blocks. So I've got sort of an oscilloscope, I've got a spectrum analyzer, I've got a signal generator, and one of the things I'm used to having on sort of like a digital oscilloscope is that ability to do a fast Fourier transform and maybe implement some filters. Is that also something that's inside this approach to instrumentation?
Yeah, so you would, I think one thing I just want to get out of the way is that, just because you are running these instruments as software modules on an FPGA doesn't necessarily mean you're making sacrifices in performance. Like we make instruments that would have the functions that you would expect. So yeah, your oscilloscope, you take a time trace, we have a math channel where you can just take the FFT of it. Spectrum analyzer has things like can calculate cross correlation. So these kind of analysis functions that you're used to with these instruments, they're there. We have the standard functionality you'd expect from these instruments, and pretty good performance as well.
Now, I was following what's been going on because I've been looking at the range of Liquid Instruments products and the software for quite a while. I've been very impressed by it. I came to one of your seminars actually in Munich a year or two ago as well. So it's really good to sort of see it in action for the first time and actually get a gauge of the size of the units as well, and the portability, especially of the smaller ones, is absolutely brilliant.
Moku is incredible. That's our smallest one. It's 2 slots and it's 2 inputs and outputs, but 30 megahertz bandwidth. But the amount of functionality you can get out of this little device.
There. Yeah,
I'd have people come up and they say, oh, well, maybe I don't have the budget for the Pro, but I just want to get one of these for myself.
Yeah, exactly. It's the sort of thing I'd have in my rucksack when I'm out and about. That's for sure.
Yeah.
And towards the end of last year, one of the things that intrigued me and the reason why I got in touch with you was that there was a sort of an introduction of an AI block for the Moko. So this is a neural network that can be used in the same place in the software environment where you'd normally deploy an FFT. Can you explain a little bit more detail how that neural network block sort of functions, where it fits in, and how people would use it?
So yeah, going back to this idea where you've got multiple slots in the so maybe show the slide after the one that you showed there. There we go. So if you're listening to this, you can imagine you partition the FPGA into 4 slots. You drop an instrument into each of these slots. You can configure your FPGA on the fly, and you don't have to. But these black lines that connect the different instruments are the ways where the signal is routed. And so you can see you can route things in and out of the device via the analog front end, which is on the bottom. But then there's also these black lines running between the instruments, and that's the digital signal. So the idea is, you can see in slot 3 there, we have the neural network. And so, you ask what that entails. So in this case, so the neural network in this case, you would actually train, you would create and you would train the network off the device. So the Moku doesn't train the network. You do that on your host PC, and you're familiar with if you're familiar with the structure of a neural network, it's basically a matrix of numbers of all your all your matrix values, and then all your activation functions, and then your biases. And so what you do on your computer then is you train the network, you wrap all those numbers up into a configuration file, and then you upload the configuration file to the Moko. And so you can see that little below the neural network icon, there's that little box with the arrow there, and that you click on that, and then that allows you to load your configuration onto the neural network. I said, so the second question would be, why would you do this? And perhaps we can get a little bit more into this. But the idea is, you don't have to go back and forth between your host PC to put data through the neural network. You've now got the neural network in the middle of your experiment chain, and you can feed data or time series data or analog voltages or anything like that through the network and get a response, kind of in real time.
Now, as I mentioned before, we're sort of used to having filtering capabilities, fast Fourier transforms, and so on. It's initially it's a really interesting and exciting capability, but what sort of measurements and instrumentation tasks can a neural network be applied to that that goes above and beyond what you'd expect from the standard types of filtering that you can build into test equipment?
So how we look at this is, as you said, we've talked about that we have in kind of output devices, we've got input devices, and we've also got a few analysis tools on the Moku. We've got filter boxes, we've got FIR filters, we've got PID controllers, and I see the neural network as kind of complementing these pretty well. The idea is it's kind of an intermediate step. It's used to kind of process data in the middle of the experimental chain, like you would with a filter, as you mentioned. So one example would be something like if you want to show the third slide. So this would be like an example. So if you open up the neural network menu, after you load this configuration onto the device, this is what you would see on the instrument. Is you've got an input. It's a time series, so it takes 32 points and it feeds it into the network. Your first layer is 16. Your next layer is 2. And basically, what this neural network is representing is what's called an autoencoder. And so what this does is it looks at data that's coming into the neural network, and it kind of breaks it down. It kind of funnels it through a very small layer, only two neurons in the second layer, and then it kind of reconstructs that signal based on the, kind of the key features that it extracts. It kind of removes all the uncorrelated noise and kind of reconstructs the signal. And so it's essentially acting like kind of a super filter. It's basically taking a signal and kind of cleaning it up. And in this case, it works really well because it can adjust in real time if there's a change in the frequency or the amplitude. Like, a low pass filter is great if you're only working at one frequency. But if you've got some kind of time varying signal that you need to keep track of and keep cleaned up, then this autoencoder does a really great job.
So what's the process then for making these neural networks? Obviously, again, going back to the FFT idea, I have a sort of number of, I can set the number of filters sort of thing, set that up and customize it to different types of filter types. How do I go about defining how this neural network should function, and what's the software process or software tools available for doing that?
So you would use so we've got several examples and walkthroughs on our website, but the basic process is that it's all done through TensorFlow through Keras, which is kind of a wrapper for TensorFlow, and you pull up Python. You use a kind of an API. So we've created this class file called LINN, LINN, Liquid Instruments Neural Network. And so you create an instance of this class file called LINN model, and then you generate your input data, you generate your training data. You just do this in Python, and then in about 5 lines, you set up your model. You define the model, so you define the number of layer. You basically have an array where each element is like the number of neurons in that layer, as well as the activation function, and then you train the model. And so basically, what it does is it feeds the input data in, it matches it against the training data, what the answer that you expect. Basically, you tell it with the training data, you tell it what the expected answer is. And then it kind of compares, it calculates that cost function. And there's other, if you want to visualize that cost function, or you want to see that evolve over time as it kind of, ideally the cost function should kind of approach, some kind of asymptotic behavior, which shows that the model is getting better and better. And I don't know, maybe I'm making this sound complicated, but it's all this happens in about 5 or 6 lines of Python code. So. Wow. We have several examples. We've got this autoencoder example, the one that I just showed. If you want to look at our GitHub or the API documentation on our website, it's quite simple. So let me just say, I think, like me as a researcher who had never used a neural network before, I think I'm the type of person that this type of instrument is aimed at, because I learned most of this as we were, preparing for the release of this instrument. So, and I think that's kind of the, actually, sorry, if I can make one more point about it's not going to be like a large language model, right? It's not, you don't need like, it's not something that you're going to need racks of GPUs to, and it's just, when you're not an FPGA, that's kind of your limitation, right?
Yeah, exactly. Yeah.
But the idea is to make something that is kind of useful for researchers and scientists, and make it easy for people who, everybody's heard of the term neural network or AI or machine learning, but how would that actually get used in the context of a research lab? That's kind of something that I've kind of learned over the last few months, and I think is quite easy for someone else in the field to pick up as well.
We've also got, I think, a slide where there's an example of how it's used to remove noise from a signal. Do you want to?
Yeah, so that's the autoencoder. Yeah, so you can show that again. So basically, what this is, okay, so this is using the Moku oscilloscope, and you can see that we've got 4 input channels on the oscilloscope here. So the first channel is the raw, kind of the raw signal. So that would be the original signal. And so then you see channel B, we add some random noise. We add a bunch of noise. We noise it up. And then channel C is basically what the signal that gets put into the neural network. It's still a sine wave, but it's incredibly noisy, doesn't look very good. And then what the neural network does, the output of the neural network is actually channel D. And so in that case, you can see that the neural network is reconstructing that sine wave. It's out producing an output that looks very clean, like the original signal, and it's removed a lot of that uncorrelated noise. And so if you're, working with any signals like this, it's a very useful feature to be able to kind of have a custom filter, in a sense, a filter that's specific to the type of signal that you're looking for. I mean, there's also situations where just a low pass or a band pass filter would work as well. But we're giving our our customers options.
Yeah, exactly. Now, talking about options, we've sort of only briefly touched on the range of Moku hardware that's available now. From memory and what you said earlier, you've got something like the small device, which has got sort of 2 inputs and 2 outputs, all the way to the Pro variant, which has got 4 inputs and 4 outputs.
Mm-hmm.
So I can also imagine then that there's sort of like the processor and FPGA hardware that's behind all of that is also a bit variable in terms of its performance. Is there sort of any limitations on the neural network depending on the piece of hardware you're using?
Well, for right now, yes. So for right now, the neural network is only available on the Moku Pro, which is our highest, the most advanced version of the model. So, and it's just all about resources, right? When you're dealing with an FPGA, I mean, they're very, the technology has come an incredibly far, but you're still, especially when you're partitioning the FPGA into 4 different, slots, you're competing for resources. And so, yeah, I mean, there are, just on the Moku Pro, there's clock speed, there's, which is kind of limits, how often the FPGA can sample. And there's also just things like, the limitation, you're limited to 5 layers with 100 activation or neurons in each layer. And, again, we think that that's, perfectly fine for basic signal processing or kind of PID-like, responding to an input and providing an output. And we think that's going to be quite, should be more than enough for a lot of applications that we're aiming for. But as you said, it's not going to, if you are deep into neural network research, this isn't going to replace your, like we said, your rack of GPUs or something. It's not going to talk to you.
Yeah, exactly. Super. Well, we've gone through all the questions that I prepared. So what I wanted to do was reach out a little bit to our audience and have a look at and see what some of the other questions are that we've got available. Now, as you said before, you're not an expert in machine learning or Python. That's something you sort of got into as this product sort of come to market. Take us a little bit through what's been your experience. How much Python did you know, for example, before you started, and how easy was it to then sort of pull all the threads together that were needed to start to build a neural network at all?
Well, so I was actually pretty experienced in Python. So like all of my graduate research was performed using kind of homebrew Python, this process I described earlier in the podcast where you're manually wrapping up a bunch of commands and just, kind of praying that it all, kind of limps across the finish line. I have found, number one, I've just found the Moku API in general to be very smooth, very, very easy to use, and just works very reliable. But as far as the neural network specifically, once you get that was actually one thing, this idea of like developing and training neural networks is something that I'd never done before. And I would say using the Moku like neural network API that we have, and this method of this class file where we create the model and we pack it in a way such that the Moku can understand, probably took me an afternoon to,
Wow. Okay.
to learn how to do. Now, let's be clear. This is just to get the model to execute from beginning to end. It does not necessarily mean training a good model, which requires a bit more experience and expertise. But to just get it to execute, yeah, I think it can be up and running extremely quickly.
Yeah, that's a good point, actually, because that brings me to another question that I've copied down here. I mean, obviously, the Moku series is well set up for capturing data from sensors and signals.
Yeah.
I mean, how does anybody go about capturing an example sensor or an example signal and then using that for training data?
So how you could do that is if you have an actual physical signal in your lab that you want to use as the training data, you could use either the Moku oscilloscope or the spectrum, any one of our data collection instruments, the oscilloscope, the spectrum analyzer, the data logger, and you can record that data. You could capture it if there's a certain pattern or if there's a certain kind of shape of a function that you're looking for. You can capture that, and then you can export that data to a CSV file. So Moku, the data logger, makes it very easy to convert between different formats. So you can put it in a NumPy array, you can put it in a CSV file, whatever is easiest for you. And then when you're building your network, when you're building and training a network, you can just import that CSV file, and then you can have that be the answer for your training model. So yeah, I would just recommend, it's a way that Moku can kind of close the entire loop there. You have your response, and then, you capture that response, and then just take it to your measurement PC.
Now, we've talked a little bit about sort of a programmable API as well for capturing some of that data, so as you can write your own software.
Mm-hmm.
Is Python the only language that's supported, or is there other languages that can be used, and sort of what are the benefits and challenges with the alternatives?
So as far as building and training the neural network goes, currently that's Python. So that's using Keras, which is a Python kind of wrapper for the neural network software. But if you're just looking to control your instrument, and you're not concerned with using the neural network instrument, we have other API support too. So first of all, we've got the native Moku app as well, our own software UI, which works incredibly well. Of course, we have Python, as I mentioned, but we also have MATLAB and LabVIEW support as well. So if you're using one of those, I'm especially not an expert with LabVIEW. I've almost never used it. From what I understand, the MATLAB works very well too, and it's very easy to install. It's quite similar in its layout and the nature of the commands, but I'm just less familiar with those two, just from my own background. But that's the idea, is like everybody uses something different. When Python might be the most popular, but there's definitely people out there that are still needing the MATLAB and the LabVIEW support.
Exactly. Yeah. No, good. There's another question here as well. In terms of sort of expertise in machine learning. I mean, if you've never done a machine learning project before, you've not really had an experience with neural networks, is this a feature that you're going to be able to get started with relatively easily based upon the demonstrations, or do you really need to maybe sort of tested the waters somewhere else before you launch into trying to put a neural network onto a Moku?
I think this offers a very kind of simple. I think the networks on here are kind of small scale, and I think that the relationship, because sometimes you're usually mapping a physical input onto a physical output, I think that can be easier to understand. If you're like me and you have to actually see the signal on a screen to kind of understand what it's doing. And so I think it's quite useful. I mean, obviously there are resources all over the internet to kind of teach you what a neural network is, what it's doing, what it's happening on the inside. We do have some walkthroughs on our website. So, we kind of designed this instrument for people that maybe would be picking it up the first time. So we've got kind of an introduction to neural networks. We've kind of got a walkthrough on how to set up and train your first network. So we do have these resources available on our website too.
Yeah, super. Well, our 20 hex minutes are almost over. One last question from my side actually would interest me. I'm more from the electronics
Mhm.
side, doing embedded systems and stuff. But when I look at some of the examples on the Liquid Instruments website, what I notice there's lots of sort of laser-based
Oh,
research
yes.
projects and things like that. Give us an example of a sort of a really interesting scientific project that you've seen use the Moko and the Liquid Instruments environment, and how what a difference it makes to the traditional approach to building that sort of experiment.
You mean the neural network specifically, or just any?
Just an example project you've seen or a customer.
We just we publish case studies all the time on our website, and one that I just saw is they need to. So one that I just wrote is they need to measure the length of an optical fiber very quickly and very precisely, and so there's commercial systems that are available for doing this. There's other methods, but none of them offer that same kind of combination of speed and precision that they need just specifically for their kind of range of optical fibers. Because you need to know how far your beam is traveling through an optical fiber. And so what they do is they use the Moku phase meter. And so they basically set up kind of an interferometer, and they kind of swept the modulation frequency like across a range, and then they were able to track that with the Moku phase meter because it can kind of automatically kind of detect the input frequency via phase lock loop. And so it was able to lock onto that frequency and kind of track across it. And so you could measure the difference in the phase as the frequency was increased. And then you just fit a line to that, and then that's the time, that's the length of your fiber, basically.
Wow.
So they found out a way to just put an optical fiber into this interferometer and measure the length of it in about 2 minutes.
Wow. How long would that sort of test normally take?
Well, so you can do it. You could do it quickly, but then you would lose a lot of the precision. It's like if you have a fiber that's on the order of some centimeters, you don't want plus or minus a centimeter,
Exactly.
uncertainty on it, right? That's okay if your fiber is kilometers long, but then you also don't want to buy a giant, commercial system that's used for testing like photonics chips or something for a fiber that's that long. Yeah. So it was, I mean, there are other avenues, but the idea, and again, I think this speaks to, what we like about the Moku is that it worked really well for them, for their specific experiment. This is what they needed, and we were able to adjust and kind of meet their needs where they were.
Yeah. Oh, fantastic. Well, Jason, it's been fascinating talking to you and learning all about the Moku as a tool in the first place, and understanding what the neural network block adds to it in terms of capability. And thanks also for being my first guest.
Yeah, well, thanks for having us on. Always fun to talk electronics. Huh?
Yeah, thanks very much. And we'll definitely see each other at the next trade fair, I'm sure.
All right. Take care, Stuart. Thank you.
Well, that's all we have time for. What have we learnt? Test and measurement was traditionally a pile of grey boxes on your workbench, an oscilloscope, a spectrum analyzer, signal generator, and so on. Today, companies like Liquid Instruments pour all of these measurement capabilities into a single box that can be configured to your testing needs. Despite this advancement, there are still some measurement challenges that aren't easily resolved using traditional analysis and filters like FFTs, but the Moku can, thanks to a neural network that can be matched to the testing challenge. And all that happens on the measurement hardware is in real time and without having to route that data via a PC or cloud service. My thanks go to Jason Ball from Liquid Instruments for sharing his test and measurement insights with us all. Don't forget to follow the Electronics Reporter for future deep tech interviews, written articles and updates. See you next time.